Hello, my name is Bonnie. I'm from Rice University. I'm glad to present this work on the topic of deep autoencoder-based sensor features for personalized prediction of mood, health, and stress. As psychologists pointed out, mental health crises can be prevented with timely interventions. According to a study in 2012, about 1/3 of major depression episodes were preventable with the existing methods. So our goal here is to help doctors determine the right timing of intervention. We can achieve that by predicting accurate well-being scores using passive sensing data. Our data were collected by effects of acute sensors, 8 Hz signals in 3 channels, namely the skin conductance, skin temperature, and acceleration. For the ground truth, email surveys were sent to the participants at 5 p.m. every day, asking for their self-assessed scores of mood, health, and stress on a continuous 100-point slide bar. Besides, there was also a pre-study screen of the participants' gender and personality. This information will be useful for clustered personalization, which will give more details later. To decompose the problem, we're essentially learning 2 projections. The first mapping is from the raw sensor data to the physiological and behavioral features, and the other from the features to prediction of the well-being scores. Autoencoders are often used for unsupervised feature learning. It learns a compressed representation of the input data by trying to reconstruct the original input from the lower dimensional latent space. Our proposed model has bottom layers locally connected, meaning that the computations were restricted to separate time frames. It can avoid over-parameterization and combat overfitting. We aggregated static features for temporal features by wrapping the hidden layers with a recurrent encoder-decoder structure, and this is based on LSTM cells. In prior to reconstructing the original data, we added Gaussian noise to the learned representations to train for more robust features. For the representation model, the personalization is done by fine-tuning the generalized representation model to each participant. Now that we have the features, we can move forward to personalized well-being prediction with multitask learning via structural regularization. Essentially, this is a linear model with F2-1 and F2 norm penalties. Multitask learning means that we need to first define what a task is. Basically, there are 2 ways of assumptions. If you assume that all users in the test set are also in the training set, then we can do user-dependent split. Otherwise, if any users in the test set are never seen by the training set, we have to do user-independent split. To accommodate for unseen users, we can make clusters of users as tasks based on their profiles, so that the model can always assign new users to the closest existing cluster and treat them as a known task. On interpretation, our goal is to let the model give explanations to humans, so that we humans can understand what features or inputs are associated with negative mental status, and so that doctors can design interventions to fix them. The representation models were evaluated by the reconstruction loss, or the mean squared errors. The prediction results were evaluated by the mean absolute errors. Here's the result of prediction errors versus the number of clusters for the 2 personalization assumptions. The overall tendencies were going down, meaning that the performance was improved by fine-grained personalization. In the end, the individualized task prediction performed significantly better than the group-based task prediction in terms of health and stress. This model compares the results of prediction performances in different sets of features. The takeaway being that the auto features works better than crafted features. Temporal auto features works better than static auto features, and using 7 days of features generally perform better than using 1-day features. Although we did see improvement of personalizing features in terms of the reconstruction loss, unfortunately, we are not seeing that improvement being transferred to the prediction here. It could be that the individual differences in self-reports were dominant over the individual differences in physiology. Then we are on to the interpretation results. In the correlation matrix between the auto and crafted features, where the correlations are high, it indicates that the auto features are closer to the corresponding crafted features. And here we list several highly correlated pairs. In this way, we can associate some physical meaning with the auto features. This work has, of course, limitations and room for improvement. Our results were solely based on a college student dataset, so that revalidation on other dataset is needed in the future. We are also actively looking into other types of data, such as phone usage, location, and weather. Further works are recommended to solve the privacy concerns and make this proposed framework to operate in real time. In conclusion, our proposed temporal representation framework can learn good well-being features, and personalization is important to realize the auto features predicting efficacy. We also emphasize the interpretability via statistical approaches and self-attention mechanism. For more details that are not covered by this presentation, please check out our full paper. Thank you.